Welcome to this mini project on building a customer churn prediction pipeline. We will combine data manipulation, cleaning, exploration, and visualization techniques. You'll take raw customer churn data and transform it into a format ready for machine learning. This course is brought to you by the Series of Thoughts Tech team. The project uses a customer churn prediction dataset, including demographics, service usage, payment details, and the churn status target variable. Our goal is to build a complete data preparation pipeline, covering loading, cleaning, feature transformation, visualization, and engineering for ML readiness. We will accomplish 5 key steps. First, load and explore the data. Second, clean the data by handling issues like missing values. Third, explore patterns using visualizations. Fourth, engineer new features and scale data. Finally, we will save the processed results. Let's begin with step 1, loading and initial exploration of the dataset. First, we import essential libraries: NumPy for numerical computing, Pandas for data manipulation, Matplotlib for foundational plotting, and Seaborn for statistical graphics and enhanced visualizations. Next, we load the data and perform initial inspection. We use !head, to check the structure, !info, to see data types and null counts, describe, for statistical summaries, and isNull.sum, to count missing values per column. During exploration, we look for data type issues, such as numbers stored as strings. We identify which columns have missing values and check for unexpected ranges, which might indicate data errors. Now we move to step 2, data cleaning, where we address the issues we identified during exploration. To handle missing numerical values, we often use median imputation, as it is robust to outliers. For example, we fill missing ages with the median age. We also critically drop rows where essential identifiers, like customer ID, are missing. We ensure data quality by removing duplicate records. We also fix data types by converting join dates to datetime objects and encoding the churn target variable from text to binary 1 or 0 for machine learning compatibility. Outliers can distort models, so we handle them using the interquartile range, or IQR method. This involves calculating Q1, Q3, and the IQR to define boundaries and remove extreme values in features like monthly underscore charges. Outlier removal matters because extreme values can pull model predictions in misleading directions, reducing accuracy. It also ensures statistical validity and addresses values that often indicate data errors rather than legitimate observations. Feature engineering transforms raw data into more meaningful variables. For example, we convert tenure_months into tenure_years and calculate AVG_monthly_charges by dividing total charges by tenure. This improves model performance by capturing key relationships. We proceed to step 3, exploratory data analysis, or EDA, to understand the processed data and identify predictive patterns. We visualize the target variable distribution using a count plot. This is critical for identifying class imbalance, which impacts model training. The percentage of the majority class sets the baseline accuracy we must beat. Histograms reveal the distribution of numerical features like age and monthly charges. We look for skewness or multimodal distributions, as heavily skewed data may require transformation to work better with certain ML algorithms. We analyze feature correlations using a heat map. Strong correlations may indicate redundancy. Features highly correlated with churn are strong predictors. We investigate unexpected patterns revealed by the correlations. Box plots compare numerical feature distributions across churn categories. By visualizing age, monthly charges, and tenure against churn, we can reveal which variables significantly differ between churned and retained customers. The box plots show that higher monthly charges indicate price sensitivity as a churn driver. Shorter tenure also correlates with higher churn, highlighting the importance of the early customer experience. Age distributions appear similar, suggesting it might not be a strong predictor alone. We analyze categorical features using count plots, comparing them against churn. This reveals categories like contract type or payment method that have disproportionately high churn rates, making them key features for the model. Key EDA insights include watching for red flags like severe class imbalance and perfect correlations. We also look for opportunities, such as strong feature target relationships and natural customer segments for stratified modeling. Next, we move into step 4, feature engineering, which finalizes the data preparation for machine learning. Machine learning models need numerical input, so we use one-hot encoding for categorical variables like contract type and payment method. The backquote drop underscore first equals true backquote parameter avoids multicollinearity by setting one category as the reference. We use standard scaler to scale numerical features like age, tenure, and monthly charges. This transforms the data to have a zero mean and unit variance. Scaling ensures that features contribute equally to the model, regardless of their original measurement scale. Feature scaling is important because unscaled features can dominate a model. Scaling centers all features at zero, allowing each to contribute proportionally. This leads to faster convergence and better performance in many models. Finally, we prepare the final dataset. We separate the features, or backquote x backquote, which are all columns except customer underscore ID and churn, from the target variable, or backquote y backquote, which is the binary churn indicator. We conclude the pipeline with step 5, saving the processed data. We export the processed data into separate CSV files for reproducibility and flexibility. We save the full dataset, the feature matrix X, and the target vector Y, ready for immediate use in downstream ML pipelines. Creating data documentation is crucial. We capture key metadata, such as the number of features and the churn rate, in a JSON file. This documentation helps track transformations, supports debugging, and ensures reproducibility. In this project, we successfully accomplished comprehensive data exploration, thorough cleaning, deep analysis, and effective feature engineering. We delivered production-ready output, including processed datasets and documentation. Key takeaways include the importance of data quality, as no model can overcome flawed data. Visualization drives insight and guides feature engineering. Feature engineering creates value, often determining model success, and documentation enables collaboration. Avoid common mistakes like skipping exploratory data analysis, using inconsistent scaling, and allowing data leakage. Remember to use domain knowledge and avoid over-engineering. Always document your pre-processing steps. Your next steps in the ML journey involve splitting your data, selecting appropriate algorithms, training and tuning models, and evaluating results using relevant metrics. Finally, you will deploy and monitor your successful model. For continued learning, explore the documentation for Pandas, Seaborn, and Scikit-learn. These resources are essential for mastering data manipulation, visualization, and machine learning techniques. You've completed a full end-to-end data preparation pipeline. Your ability to execute this confidently demonstrates that you understand the reality of data science. Preparing data is the foundation of successful modeling. Practice this workflow to build your data intuition.